Hello, and welcome to tonight's Space Sleep Story. If you appreciate what we do here, please like or subscribe for future relaxing nighttime space journeys. Tonight, we embark on a journey not through space, but through time. 5,000 years of human curiosity about Mercury, the elusive planet that has challenged observers from ancient Sumerian astronomers to modern spacecraft engineers. So settle into your most comfortable position, close your eyes, and prepare to trace humanity's patient investigation of the mysterious jumping planet. Before we begin, let us prepare your body and mind with gentle breathing. Take a slow, deep breath with me now. Inhale gently for 4 counts. Hold the peace. Exhale for 6. Feel your body releasing into stillness. Let the ancient story of Mercury observation wash over you like a gentle tide. Each breath brings you deeper into relaxation. Another gentle breath as we continue our preparation. This time, notice how your chest rises and falls, like the endless cycle of celestial observation across millennia. Inhale peace. Hold this peaceful moment. Exhale the stress of modern life. Feel yourself connecting with those ancient observers who looked up at the same wandering light in the twilight sky 5,000 years ago. With each breath, you release a little more into relaxation. We begin in ancient Mesopotamia, circa 3000 BCE. Sumerian astronomers recording observations on clay tablets, writing in cuneiform script the name udu.idim.gud.ud, meaning jumping planet. Mercury's rapid motion through the sky, appearing and vanishing in twilight, faster than any other celestial wanderer. These patient observers had no telescopes, no mathematical models, just naked eyes and dedicated attention. Night after night, year after year, century after century, they watched and recorded. Mercury completes one full orbit around the Sun in 87.97 Earth days. Traveling at 47.87 kilometers per second, it is the fastest moving planet in our solar system. This extraordinary speed made Mercury jump from evening star to morning star faster than Venus, Mars, Jupiter, or Saturn. Ancient observers noticed this peculiar behavior, this rapid disappearance and reappearance. The jumping planet earned its Sumerian name through simple observation and wonder. But Mercury presented ancient astronomers with a fundamental challenge. It never appears more than 28 degrees from the Sun, as seen from Earth. Venus can reach 47 degrees elongation, appearing high in dark sky after sunset or before sunrise. The outer planets can appear anywhere in the night sky, even opposite the Sun at midnight. Mercury remained forever trapped in twilight, visible only briefly near the horizon when the Sun had just set or was about to rise. Fleeting glimpses in difficult viewing conditions. Ancient Greek astronomers before 500 BCE faced this twilight puzzle. They saw a bright object in the eastern sky before sunrise, swift and brilliant. They called it Apollo. They saw another bright object in the western sky after sunset, equally swift and brilliant. They called it Hermes. Two different celestial bodies, they reasoned. After all, they never saw both simultaneously. How could one object be in two places? The limitation of observation led to reasonable but incorrect conclusion. Around 500 BCE, the Greek philosopher Heraclitus of Ephesus made a crucial insight. He recognized that Apollo and Hermes were a single object. The same rapid motion pattern, the same brilliance, the same proximity to the sun. Never visible together because they were the same wandering star appearing in different parts of its cycle. Through logical deduction from patient observation, Heraclitus unified understanding. One planet, two appearances. Morning star and evening star, both Mercury. Knowledge advancing through careful thought. The Babylonians conducted systematic Mercury observations for 8 centuries. From 747 BCE to 61 CE, they maintained astronomical diaries on clay tablets, recording Mercury elongations, conjunctions with other planets, appearances and disappearances. 800 years of continuous observation, generation after generation of astronomers building upon their predecessors' work. These tablets survived millennia, preserved in archives, providing later astronomers with invaluable data spanning centuries. Patience and dedication creating lasting scientific value. Around 150 CE, Claudius Ptolemy compiled centuries of observations into his great work, the Almagest. Using data from Timocharis, who observed Mercury around 290 BCE, and others spanning 400 years, Ptolemy created a geocentric model, with Mercury traveling on an epicycle, a small circle, whose center orbited Earth on a larger circle called the deferent. Complex geometry, but it worked. The model predicted Mercury positions with remarkable accuracy. Wrong framework, correct mathematics. Ptolemy's model guided astronomers for 14 centuries. Timocharis, the Greek astronomer from Alexandria, reflected on his decades of observation. The wandering stars reveal their nature slowly, he understood. One must observe many years, recording positions against the fixed stars before patterns emerge. Mercury especially demands patience. Fleeting appearances in twilight, rapid motion, unpredictable schedule. Yet systematic records accumulate understanding where single observations bring only confusion. His measurements, made around 290 BCE, were used by Ptolemy 400 years later. Knowledge transcending individual lifetimes. In 1543, Nicolaus Copernicus published De Revolutionibus Orbium Celestium. He placed the Sun at the center, with Mercury as the innermost planet. This heliocentric model greatly simplified explaining Mercury's behavior. Why does Mercury never stray far from the Sun? Because it orbits closer to the Sun than Earth does. Why does it show retrograde motion? Because Earth's orbit is larger, occasionally overtaking the inner planet. What geocentric epicycles made complex, heliocentric geometry made beautifully simple? Mercury's motion explained by position, not by complicated mathematical machinery. Johannes Kepler discovered in 1609 that planetary orbits are ellipses, with the Sun at one focus. Mercury's orbit proved the most elliptical of all planets. Its eccentricity measures 0.206, meaning the distance from Sun varies from 46 million kilometers at closest approach to 70 million kilometers at farthest point. This explained Mercury's variable speed through the sky and its changing apparent size through telescopes. Perfect circles cannot account for Mercury's behavior. Nature chooses elegant mathematics over perfect forms. On November 7, 1631, Pierre Gassendi made history. Using predictions from Kepler's tables, he observed the first Mercury transit across the Sun's disk. A small black dot moving across the solar surface during several hours. "This morning I witnessed what no human before me has seen," Gassendi wrote. Mercury crossing the Sun's face as predicted. Kepler's mathematics forecast this rare event, and nature obliged precisely. The power of mathematical astronomy to predict celestial phenomena filled observers with wonder at human reason's reach. Knowledge enabling prediction, prediction validated by observation. In the 1610s, Galileo Galilei observed Mercury through his early telescope. Magnifying 8 to 30 times, he detected phases like the Moon. Crescent phase, when Mercury appeared near inferior conjunction between Earth and Sun. Gibbous phase, when near superior conjunction on the far side of the Sun. These phases provided crucial evidence that Mercury orbits the Sun, not Earth. A geocentric model predicts no full phase cycle, but a heliocentric model requires exactly the phases Galileo observed. Direct visual confirmation of Copernican theory through patient telescopic observation. As centuries progressed, telescopes grew larger and more sophisticated. Astronomers attempted to map Mercury's surface features, seeking to determine its rotation period. But Mercury's small, apparent size, its low altitude near the horizon, and atmospheric turbulence at low angles conspired against detailed observation. Brief glimpses of possible features, gone in seconds when atmospheric steadiness failed. Delicate albedo variations, perhaps indicating continents or maria, but nothing definitive, nothing certain. Mercury guarded its secrets well against telescopic observers. Between 1881 and 1889, Giovanni Schiaparelli conducted careful Mercury observations from Milan. Using a 22-centimeter refractor during rare, excellent seeing conditions, he mapped surface features. Dark and bright regions, forming patterns that he meticulously sketched and recorded. These same features appeared in the same positions during apparitions, separated by Mercury's 88-day orbital period. Schiaparelli concluded Mercury rotates synchronously with its orbit. Like the Moon showing one face to Earth, Mercury would show one face to the Sun. Permanent day side, permanent night side, twilight zone between. Schiaparelli's synchronous rotation conclusion was reasonable from available observations. A careful scientist making logical deduction from difficult data. The astronomical community accepted this finding. Textbooks incorporated it. Planetarium shows presented it. NASA planning documents assumed it. From 1889 to 1965, for 76 years, humanity believed Mercury was tidally locked. One face forever toward the sun at 430 degrees Celsius, the opposite face forever in frozen darkness at negative 180 degrees. A seemingly established fact, built on careful observation. But observation has limits. In the 1920s, French astronomer Eugene Antoniadi used the Meudon Observatory's 83-centimeter refractor, the largest telescope yet applied to Mercury observation. During hundreds of apparitions, waiting for brief moments when atmospheric turbulence calmed, he refined Schiaparelli's maps. Through the large refractor, he glimpsed delicate details, albedo variations, possible features, gone in seconds when the air steadied again. He confirmed Schiaparelli's synchronous rotation conclusion. Mercury observation tests the astronomer's patience and skill, Antoniadi reflected. We need new methods beyond telescopes. While telescopic observers struggled with Mercury's rotation, mathematical astronomers discovered a different mystery. In 1859, French astronomer Urbain Le Verrier calculated that Mercury's perihelion, its closest point to the Sun, advances 43 arcseconds per century beyond all known gravitational influences. Newton's theory predicted Mercury's perihelion precession based on perturbations from Venus, Earth, Mars, Jupiter, and Saturn. The prediction: 5,557 arcseconds per century. The observation: 5,600 arcseconds per century. 43 arcseconds unexplained. A tiny discrepancy pointing to profound mystery. Le Verrier had successfully predicted Neptune's position from Uranus perturbations a decade earlier. Mathematical astronomy had triumphed spectacularly when Neptune was discovered almost exactly where Le Verrier calculated it should be. He applied the same method to Mercury's anomaly. If an unseen planet perturbed Uranus, perhaps another unseen planet perturbed Mercury. He proposed Vulcan, orbiting inside Mercury at 0.28 astronomical units, completing an orbit every 19.7 days. Mathematics predicted Neptune hiding beyond Uranus. The same method now pointed to Vulcan hiding inside Mercury's orbit. Reasonable extrapolation from proven technique. In March 1859, French amateur astronomer Edmond Lescarbot reported observing a dark spot crossing the Sun. Le Verrier interviewed him, calculated a Vulcan orbit, and announced the discovery to the astronomical world. Professional astronomer James Watson claimed spotting Vulcan during the total solar eclipse of July 29, 1878, from Wyoming. Multiple eclipse expeditions organized specifically to search for the hypothetical planet. Astronomers photographing the Sun's corona during totality, looking for unknown worlds. But despite decades of searching, no consistent Vulcan detections were achieved. The planet remained stubbornly invisible. By the early 20th century, skepticism grew. American astronomer Simon Newcomb analyzed 20 years of Vulcan claims. Despite expeditions and amateur sightings, no reproducible observations exist, he concluded. Perhaps Mercury's anomaly has a different explanation than an intramercurial planet. Perhaps our understanding of gravitation requires refinement at such proximity to the Sun's mass. Newcomb's skepticism proved prescient. The answer would come not from discovering a new planet, but from discovering new physics. Sometimes, the right scientific method addresses the wrong problem. In 1915, Albert Einstein published his general theory of relativity. Gravity, he proposed, results from massive objects curving space-time itself. Planets orbit the Sun not because an invisible force pulls them, but because they follow curved paths through warped space-time. Einstein calculated Mercury's perihelion precession using general relativity. The prediction, exactly 43 arc-seconds per century additional precession due to space-time curvature near the Sun's enormous mass. The observation, 43 arc-seconds unexplained by Newtonian physics. Perfect agreement. Vulcan vanished not because it was found, but because it became unnecessary. Mercury's anomaly transformed into one of the first confirmations of general relativity. The Vulcan hypothesis taught valuable lessons. Mathematical prediction had succeeded brilliantly with Neptune. The same method applied to Mercury seemed logical. But the anomaly required new physics, not a new planet. Failed hypotheses are not scientific failures. The search for Vulcan pushed observational techniques forward, motivated eclipse expeditions, and ultimately revealed the limits of Newtonian gravity. A productive failure that pointed toward relativity. Science advances through both confirmation and correction. Each generation builds on previous understanding, sometimes confirming, sometimes revising, always advancing. Through the first 6 decades of the 20th century, Mercury's synchronous rotation remained accepted fact. Astronomy textbooks described permanent day and night hemispheres. Science fiction stories imagined life in the twilight zone between eternal heat and eternal cold. NASA engineers planned missions assuming one face always toward the Sun. Then, in April 1965, everything changed. Gordon Pettengill and Rolf Dice at Arecibo Observatory in Puerto Rico bounced radar signals off Mercury. The reflected radio waves carried information about rotation. Doppler shift revealed motion toward and away from Earth. The data indicated a rotation period of 58.646 days, not 88 days. Immediate shock rippled through the astronomical community. Textbooks wrong for 76 years. Pettengill contacted Italian scientist Giuseppe Colombo, known as Bepi. Within hours, Colombo recognized the significance. 58.646 divided by 87.97 equals exactly 2/3. Mercury rotates 3 times during 2 orbits. A 3-to-2 spin-orbit resonance. Tidal locking couldn't capture Mercury 1-to-1 because the elliptical orbit varies tidal strength throughout the orbit. Instead, the planet settled into a stable 3-2 configuration. This resonance explained why Schiaparelli saw the same features every 88 days. Every 2 Mercury years equal 3 Mercury rotations, repeating the geometry. Colombo marveled at nature's elegant mathematics. Mercury spins 3 times per 2 orbits, he explained. The elliptical orbit prevents simple 1-to-1 tidal lock. The planet settled into 3-2 resonance instead. This creates a solar day on Mercury of 176 Earth days. Sunrise to sunrise takes exactly 2 Mercury years. Mathematics reveals nature's elegant solutions to gravitational puzzles. One radar measurement overturned nearly a century of assumed knowledge. This is why we build new instruments, Pettengill reflected. Every assumption deserves testing with better tools. Technology enabling truth. The radar astronomy revolution continued beyond rotation period. Throughout the 1970s, 80s, and 90s, Arecibo and Goldstone Deep Space Network antennas conducted systematic Mercury observations during favorable apparitions. Doppler shifts and time delays built crude surface maps showing crater distributions and surface roughness. In 1991, radar detected bright reflective deposits in Mercury's polar regions. Permanently shadowed craters near the north and south poles showed radar signatures consistent with water ice. A surprising discovery on the planet closest to the Sun. Radar astronomy revealing secrets invisible to optical telescopes. While radar transformed ground-based Mercury observation, spacecraft prepared to journey there directly. In November 1973, NASA launched Mariner 10. This mission pioneered the gravity assist technique, flying by Venus in February 1974 to use gravitational slingshot reaching Mercury. Mariner 10 conducted 3 Mercury flybys: March 29, 1974, September 21, 1974, and March 16, 1975. The spacecraft mapped approximately 45% of Mercury's surface, revealing heavily cratered terrain resembling the Moon, the enormous Caloris Basin impact structure, and lobate scarps indicating planetary contraction. But orbital resonance limited coverage, leaving 55% unmapped. Mariner 10 made an unexpected discovery. Mercury possesses a magnetic field. No one predicted this. Magnetic fields require molten iron cores, with convection currents generating dynamo action. Mercury seemed too small to maintain internal heat for a molten core. Yet the magnetometer detected a field strength of 300 to 400 nanoteslas, about 1% of Earth's field. Mercury revealed itself as more geologically active and complex than anyone expected. Direct observation overturning theoretical assumptions. The value of going there, seeing for ourselves, measuring directly. "33 years passed between Mariner 10's last flyby and the next Mercury mission. In August 2004, NASA launched MESSENGER, Mercury Surface, Space Environment, Geochemistry, and Ranging. Reaching Mercury orbit required 7 years of interplanetary travel. 6 planetary flybys, 1 Earth, 2 Venus, 3 Mercury. Each flyby using gravity to reshape the trajectory, shedding orbital energy incrementally. The most complex trajectory ever flown at that time. On March 18, 2011, Messenger became the first spacecraft to orbit Mercury. A technological and navigational triumph 7 years in the making. Patience and precision culminating in orbit insertion. For 4 years, Messenger circled Mercury. The spacecraft conducted 4,105 orbits, imaging 100% of the surface at high resolution. X-ray and gamma-ray spectrometers mapped elemental composition across the entire planet. Magnetometers characterized the magnetic field in detail, revealing unexpected asymmetry. Messenger confirmed the radar-detected polar ice deposits as water ice, preserved in permanently shadowed craters. The mission discovered mysterious features called hollows, bright, irregular depressions unique to Mercury. Comprehensive understanding replacing incomplete knowledge. On April 30, 2015, Messenger ended its mission with controlled impact on Mercury's surface. 4 years of operation, exceeding all expectations. Sean Solomon, Messenger's principal investigator, reflected on the mission's achievements. Before Messenger, Mercury was the most poorly understood terrestrial planet, he noted. Half its surface unmapped, composition unknown, ice hypothetical, magnetic field unexplained. After 4 years orbiting, we imaged every square meter, mapped elements globally, confirmed ice, characterized field asymmetry. Yet mysteries remain. That is exploration. Mariner 10 opened Mercury's door. Messenger walked through. Each generation advances understanding. None completes it. Science is a relay race across decades, not a sprint. In October 2018, the European Space Agency and Japan Aerospace Exploration Agency launched BepiColombo. This ambitious mission carries 2 spacecraft, Mercury Planetary Orbiter and Mercury Magnetospheric Orbiter. Reaching Mercury required 9 planetary flybys, 1 Earth, 2 Venus, 6 Mercury. The complex trajectory finally achieved orbit insertion in December 2025. BepiColombo will provide the first simultaneous surface and magnetosphere measurements, stereo imaging, and improved compositional mapping. The mission honors Giuseppe BepiColombo, the Italian scientist who recognized Mercury's 3:2 resonance hours after the 1965 radar discovery. International collaboration continuing Mercury investigation into the mid-2030s. "5,000 years of observation." From ancient Sumerian cuneiform tablets recording the jumping planet, to spacecraft orbiting and imaging every crater, ancient observers tracked motion across the sky with patient, naked-eye attention. Renaissance mathematicians calculated elliptical orbits, enabling accurate predictions. Telescopic astronomers mapped surface features, reaching careful but incorrect conclusions about rotation. Theoretical physicists explained orbital anomalies with new understanding of gravity and space-time. Radar astronomers corrected 76 years of error with a single measurement. Spacecraft engineers navigated complex trajectories to orbit Mercury, imaging and measuring comprehensively. Each generation contributed essential pieces. Babylonian 8th century observational records provided data for Ptolemy's mathematical model 400 years later. Kepler's elliptical orbit calculations enabled Gassendi to observe the predicted 1631 transit. Einstein's relativistic physics explained the anomaly Le Verrier attributed to Vulcan. Schiaparelli's maps showed real features despite incorrect rotation period. Colombo's 3-to-2 resonance insight explained why Schiaparelli saw what he saw. Ancient observations enabled Renaissance mathematics. Renaissance mathematics enabled spacecraft trajectories. Each contribution necessary, none sufficient alone. Knowledge building across millennia through patient accumulation. Consider the timescales of understanding. Heraclitus unified morning star and evening star in his lifetime, around 500 BCE. Schiaparelli's rotation error persisted 76 years before correction. The Vulcan hypothesis motivated searches for 56 years before Einstein's relativity explained the anomaly differently. Babylonian astronomical diaries spanned 800 years of continuous observation. Some mysteries resolve quickly through insight. Some persist decades, awaiting better instruments. Some require centuries of data accumulation. All eventually yield to patient investigation and technological advancement. Science operates on timescales far exceeding individual human lives. Observational limits can sustain errors for generations. Schiaparelli and Antoniadi were careful, skilled observers, making reasonable conclusions from difficult data. Mercury low on the horizon, atmospheric turbulence severe at low altitudes, surface contrast minimal, apparitions brief. They saw real features and interpreted patterns logically. But synchronous rotation was incorrect, not because of poor observation, but because observation alone had limits. New technology, radar astronomy, immediately revealed truth. Doppler shift in reflected radio waves, measuring rotation period definitively. Sometimes old questions await new instruments. Patience and technological progress together advancing understanding. Failed hypotheses teach valuable lessons. Le Verrier's Vulcan hypothesis proved incorrect. No planet orbits inside Mercury. But the search motivated eclipse expeditions, advancing observational techniques. It demonstrated the limits of Newtonian gravity near massive objects. It pointed toward the need for general relativity. Mercury's anomaly became one of Einstein's first confirmations. A hypothesis can be scientifically valuable, even if ultimately wrong. Vulcan failed as a planet, but succeeded as a scientific catalyst. Wrong answers sometimes ask the right questions, guiding investigation toward deeper truth. International collaboration built Mercury understanding. Sumerian, Babylonian, Greek, Islamic, European, American, Japanese observers across cultures and centuries. Ancient Mesopotamian astronomers recorded motion. Greek philosophers unified morning and evening appearances. Islamic astronomers refined orbital parameters during the medieval period. European telescopic observers mapped features. American radar astronomers corrected rotation period. International spacecraft missions imaged comprehensively. Knowledge transcends borders and generations. Mercury understanding belongs to humanity collectively, not to individuals or nations. A truly global, multi-generational achievement. Technology enables discovery. Naked eyes tracked Mercury's rapid motion, leading to Sumerian jumping planet observations. Telescopes revealed phases, confirming heliocentric model. Large refractors mapped surface features, though rotation remained uncertain. Radar astronomy measured rotation definitively, overturning decades of error. Spacecraft imaged surface comprehensively, discovered magnetic field unexpectedly, confirmed ice deposits. Each technology generation answered questions previous generations couldn't. Sometimes patience means waiting for instruments that don't yet exist, building tools to reveal nature's hidden truths. Your breath connects you to this ancient lineage. Breathe in slowly, 4 counts. Hold. Exhale, 6 counts. Sumerian astronomers breathed the same rhythm, watching Mercury in twilight 5,000 years ago. Schiaparelli breathed steadily at the telescope eyepiece. Pettengill breathed with anticipation, as radar data revealed true rotation. Spacecraft engineers breathed with relief as Messenger achieved orbit. Your breath joins theirs across time. Observation, wonder, investigation, understanding. The endless human reaching toward cosmic knowledge. Tonight, rest in the knowledge that Mercury's story demonstrates science's patient accumulation. 5,000 years from mysterious wandering light to comprehensively understood world. Ancient observers couldn't imagine spacecraft would orbit Mercury, but they contributed essential foundation. Their observations enabled Kepler's orbits. Kepler's orbits enabled spacecraft trajectories. Spacecraft revealed comprehensive truth. Knowledge is a relay race. Each generation carries understanding forward. You rest tonight as inheritor of 5 millennia of curiosity. Tomorrow, investigation continues, as it always has, as it always will. Mercury orbits the Sun. 87.97 days per revolution. Same period when Sumerians first recorded it. Same period tonight. Human understanding changed. Mercury's motion changed nothing. We observe, we learn, we pass knowledge forward. Antimacaris measured positions. 290 BCE. Ptolemy used his data. 400 years later. Knowledge transcending individual lifetimes. Building across generations. Patient accumulation of understanding. Schiaparelli observed carefully. Reached incorrect conclusion. Science corrected itself. 76 years later. Errors teach lessons. Better instruments reveal truth. Self-correction demonstrates science working. Le Verrier proposed Vulcan. Searched 56 years. Einstein explained differently. New physics, not new planet. Wrong hypothesis, valuable catalyst. Pointing toward relativity. Failure as progress. April 1965. Radar revealed true rotation. Single measurement correcting decades. Technology enabling truth. Colombo recognized ratio. 3:2 resonance. Mathematics revealing elegant solutions. Mariner 10 imaged Mercury. 1974, 45% mapped. First spacecraft visit. Messenger orbited 4 years. 100% imaged. Comprehensive understanding achieved. BepiColombo arrived. December 2025. Investigation continuing. International collaboration. $5,000-year journey. Mystery to understanding. Patient investigation across millennia. Ancient tablets, Renaissance mathematics, modern spacecraft, all contributing essential pieces. Knowledge belonging to humanity, transcending borders and centuries. Global, multi-generational achievement. Sumerian observers. 3000 BCE. Watching jumping planet. Same planet tonight. Your curiosity connects you. Ancient lineage of observers. 5 millennia of wonder. Babylonian diaries. 800 years recorded, generation after generation, building data set patiently. Small observations matter, accumulating into understanding. Each contribution necessary. Copernicus simplified motion. 1543. Heliocentric model explaining what epicycles made complex. Kepler discovered ellipse. 1609. Nature's elegant mathematics. Gassendi witnessed transit. November 1631. First human seeing this. Prediction confirmed. Galileo observed phases. 1610s. Heliocentric proof. Each discovery building on previous understanding, sometimes confirming, sometimes correcting. Always advancing. Relay race across time. Never completing. Sean Solomon reflected. Science is relay race, not sprint. Generational effort. Tonight you rest in that ancient lineage, observer and inheritor. Mercury keeps orbiting. Same period. Same path. Unchanged by observation. Human understanding transformed from mystery to knowledge. 5,000 patient years. Tomorrow, investigation continues. New instruments, new questions, new understanding. as it always has, as it always will, forever. Sleep peacefully in knowledge of patience. Multi-generational wonder, ancient, ongoing investigation. You participate in timeless human curiosity, observing cosmos we inhabit. Rest now. Deep, peaceful rest. 5,000 years watching. Mercury still shining. Tonight, tomorrow, forever. Babylonian astronomers recorded observations 800 years. Generation after generation watching Mercury, building dataset patiently. Each observer contributed without knowing future impact. Small measurements accumulating into comprehensive understanding. Knowledge builds slowly. Copernicus placed Mercury innermost. 1543 heliocentric model. Simplifying what epicycles made complex. Kepler discovered Mercury's elliptical orbit, most eccentric of all planets. Nature choosing elegant mathematics. Gassendi witnessed first transit. November 1631. Prediction confirmed by observation. Galileo observed Mercury's phases through telescope. Proof of heliocentric model. Direct visual evidence. Each discovery validating previous theories, sometimes confirming understanding, sometimes requiring revision. Schiaparelli mapped Mercury carefully, 1889. Reasonable conclusion from difficult data. Error lasting decades. Antoniadi confirmed synchronous rotation. Larger telescope, same conclusion. both observers skilled and careful. Observational limits sustained the error. Mercury, low on horizon always. Atmospheric turbulence, severe. Le Verrier calculated perihelion anomaly. 43 arcseconds unexplained. Mathematics pointing toward mystery. Vulcan hypothesis seemed logical extension. Neptune predicted successfully before. Same method applied. Eclipse expeditions searched for Vulcan. 56 years of looking, never finding consistent evidence. Einstein explained anomaly differently, 1915. Space-time curvature near Sun. Relativity confirmed. Vulcan taught valuable lesson. Right method, wrong problem. Productive failure pointing toward truth. April 1965 changed everything. Arecibo radar revealed true rotation. Single measurement. Pettengill and Dice measured 58.6 days. Not 88. 76-year error corrected. Colombo recognized ratio immediately. 3:2 resonance. Elegant gravitational mechanics. Mercury spins 3 times during 2 orbits. Perfect mathematical harmony. Mariner 10 flew by 1974. First spacecraft imaging. 45% mapped. Magnetic field discovered unexpectedly. Nobody predicted this. Direct observation revealing. Messenger orbited 4 years. 2011 to 15. Complete surface imaging. "100% mapped. Every crater recorded. Comprehensive understanding achieved." Polar ice confirmed. Water preserved forever. Closest planet to Sun. BepiColombo continues investigation. International collaboration. Europe and Japan together. Five millennia of observation. Mystery to understanding. Patient accumulation. Ancient observers start a journey. Modern scientists continue, never truly complete. knowledge belongs to humanity, transcending all borders, crossing all centuries. Your curiosity connects you to ancient lineage, 5,000 years. Sumerian astronomers watched. Same planet you see tonight. Breathe with history. Deep, peaceful breath, connecting across time. Timocharis measured positions. Ptolemy used data. Centuries later, each contribution matters. Building understanding, generation by generation. sleep in this knowledge. Patient investigation reveals cosmic truth. Mercury keeps orbiting, unchanged forever. Human understanding transformed.